Welcome to the deep dive. Today we're plunging into, well, a truly astonishing story. Imagine a world where the idea of a thinking machine was just pure fantasy almost 200 years ago.
Yeah.
Yet here we are, surrounded by computers so commonplace we barely even notice them.
It's incredible, isn't it? To think that initial spark of imagination almost 2 centuries back really laid the groundwork for our entire digital world. This deep dive is all about uncovering those surprising insights and, the winding path from that initial dream to the reality we live in now.
Absolutely. Our mission today is to take you on a journey through the visionary but ultimately unfinished invention of Charles Babbage, his analytical engine.
A machine profoundly ahead of its time.
Totally. We'll unpack its radical design, explore the essential building blocks that, eventually led to modern computers, and reveal the pivotal moments and the unsung heroes and heroines
Right.
who really shaped the digital landscape we inhabit.
Yeah, there are quite a few.
You'll gain a real shortcut, hopefully, to understanding this complex evolution of computing.
It's a tale of remarkable genius for sure, but also of lucky coincidences, unexpected missteps, and interestingly, countless reinventions that ultimately propelled us to these astonishing breakthroughs.
So before we jump right into Babbage's specific genius, it's probably worth taking an even longer view, because the human desire to compute, to calculate, isn't new at all. We've been figuring things out for millennia, right?
Oh, precisely. If you go back thousands of years, basic calculation methods were incredibly inventive. I mean, people used pebbles for counting, notches and sticks, knots and cords, even marks on clay tablets.
Simple stuff, but effective.
Simple, effective, and it just shows that our drive for organized computation has always been there, deep-seated.
And mechanical aids, things beyond just pebbles, they actually predate Babbage by quite a bit, too.
Yeah.
What are some of the, standout early examples?
Well, the slide rule is a big one. Developed by Englishmen Edmund Gunter and William Oughtred way back in 1650, and later improved by Amede Amheim. It was a super practical tool for calculation for centuries.
Right, engineers used those for a long time.
They did. But for something truly mind-blowing from antiquity, you have to look at the Antikythera mechanism, found dating from around 100 BC.
The Antikythera mechanism. Oh man, this one always gets me. Discovered in 1901, right? Believed to be the earliest known geared computing device.
That's the one, an astronomical calculator, incredibly sophisticated for its time.
It just reinforces that complex mechanical computation wasn't some sudden 19th century idea out of nowhere.
Exactly. Which brings us nicely to the visionary himself, Charles Babbage. Let's delve into his work. He's often credited, as the father of the computer, but his story is also one of magnificent, kind of unfulfilled potential.
Okay, let's unpack this. So before his really radical analytical engine, Babbage actually started with something called the difference engine. This was a simpler mechanical calculator designed specifically to tabulate mathematical functions like logarithms and trigonometric tables using this method called finite differences.
Yeah, and those tables, by the way, were absolutely critical for fields like engineering and navigation, vital at the time. But the human computers, actual people doing the calculating, they were notoriously prone to error.
I can imagine. Tedious work.
Incredibly tedious. So Babbage, being a brilliant mathematician, saw all these inconsistencies and basically reasoned that a machine could do the job with far greater accuracy.
Makes sense.
He even partially funded its construction himself and managed to secure a government grant, which shows that, public investment in computing is hardly a new concept.
Not true.
But a significant conflict with his chief engineer, Joseph Clement, and then the British government pulling the funding meant the difference engine was never fully completed.
And you could argue maybe he should have stuck with it, gotten that one finished.
Perhaps. But Babbage, well, he was Babbage. He moved on because he had an even grander, more ambitious idea brewing. By 1837, he'd conceived of the analytical engine.
Right.
And this wasn't just a calculator. This was conceived as a digital mechanical general-purpose computer. A massive leap.
Okay, here's where it gets truly fascinating. Its design included components that are, well, strikingly similar to what we see in modern computers. He envisioned a store, which was its memory, designed to hold 1,000 numbers, each with 40 decimal digits.
40 digits. That's roughly equivalent to, 16.6 kilobytes of data today in the 1830s?
And it's nuts. So imagine, nearly 2 centuries ago, Babbage envisioned memory, just like your computer has RAM. And it also had what he called the mill, its arithmetic unit.
The processor, basically.
Yeah. The mill could perform all four basic arithmetic operations, comparisons, even square roots optionally. Think of the mill as the equivalent of a modern CPU, the central brain.
And even more remarkably, it had internal procedures, like miniature built-in instructions for the machine's core operations, stored on these rotating drums with pegs called barrels, kind of like early microcode.
Wow, and input-output.
Punched cards, just like those looms we mentioned earlier. You'd have operational cards for instructions and variable cards for the data. But the truly groundbreaking feature, I mean, a century ahead of its time, was its ability for user programs to loop.
Ah, branching.
Exactly. The cards could be directed to move forward and reverse, allowing for conditional control transfers and repeating sequences. This was a level of programmability simply unmatched by anything conceived before it.
So this incredibly sophisticated design, why didn't it get built? It feels almost tragic that Babbage was never able to complete construction of any of his machines.
Yeah, those ongoing conflicts and, again, the lack of adequate funding just couldn't get it over the line.
And the sheer impact of that unbuilt machine is startling when you think about it. It wasn't until 1941 that Konrad Zuse in Germany built the first working general-purpose computer, the Z3.
More than a century later.
More than a century after Babbage proposed the analytical engine.
And this brings us to another absolutely critical figure in this story, Ada Lovelace.
Right, Lord Byron's daughter.
The very one. Ada was a talented mathematician who, unlike many of her contemporaries, truly grasped the depth of Babbage's vision. She wasn't just looking at a calculator.
She saw the potential.
She saw the potential. She published a detailed description of the analytical engine and, crucially, appended notes, including a hypothetical program designed to calculate Bernoulli numbers.
Which is now seen as
Widely considered the first example of a true computer program, making her, effectively, the world's first conceptual programmer.
Okay, so here's where the story takes a bit of a surprising, almost frustrating turn. Despite this visionary work by Babbage and Lovelace, his ideas largely fell into historical obscurity for a long time.
Yeah, they didn't really catch on immediately. Later pioneers, people like Howard Aiken, who built the electromechanical Harvard Mark this ray between 1937 and 1945.
A huge machine in its own right.
Massive. But Aiken was apparently unaware of the details of the analytical engine's architecture. He praised Babbage generally, sure, but he famously visited the constructed portion of the analytical engine and called it the greatest disappointment of my life because he just didn't grasp the underlying revolutionary design principles. He saw gears, not the concept.
Wow. So that lack of awareness meant many of Babbage's architectural innovations basically had to be reinvented by others later on.
Pretty much, yeah. For example, that Harvard Mark I, despite its enormous size, 51 feet long, 8 feet high, weighing 5 tons, it notably lacked conditional branching.
The looping feature Babbage had designed.
Exactly. A feature Babbage had designed a century earlier. And similarly, J. Presper Eckert and John W. Mauchly, the guys who designed ENIAC, they also started their work without knowledge of Babbage's detailed plans, essentially retracing steps Babbage had already envisioned conceptually.
Okay, so if Babbage was building these amazing mechanical computing devices, what was the foundational leap in logic that changed everything for electronic computers? That takes us to George Boole, right, back in the 19th century.
That's right. The brilliant mathematician George Boole, his big idea was really elegant. Represent information using just 2 logic states, true or false, on or off, 1 or 0.
Binary.
Essentially, yeah. He developed a whole system of mathematics, formulas for calculations based purely on this 2-state information. We now call it Boolean algebra.
But what's truly remarkable is how long these ideas just kind of sat there.
Right. For most of a century, Boole's mathematical ideas remained largely unknown, or at least unused in any practical engineering sense. It wasn't until 1937, that's nearly 75 years after Boole's death,
Wow.
that Claude Shannon, who was then an MIT student, recognized the profound connection
Between what?
between electronic circuits and Boolean algebra. He showed how you could assign different voltage levels, high voltage, low voltage, to represent Boole's true-false states.
The physical implementation.
Exactly. The on-off functions of switches in electronic circuits could directly map to Boolean logic. This discovery became an absolute cornerstone of digital electronic design. It's fundamental to every single digital device around you today.
So Boolean logic provided the language. But what about actually processing data before electronics really took over? This is where Herman Hollerith comes in, right, with the U.S. Census.
Yeah, Hollerith made a huge impact. In the late 1800s, America's population was just exploding, and manually tallying the U.S. Census was becoming this impossible logistical nightmare. Took years.
So Hallworth developed these tabulating machines using punched cards again.
Punched cards again, and electricity. He used them to process the data for the 1890 U.S. Census.
And the results.
Astonishing leap forward. The census results, which previously took like 8 years,
8 years.
were tallied in just 6 weeks.
Wow, that's a game changer for government.
Huge. And Hallworth's tabulating machine company eventually merged with others to form, well, what we know today as IBM.
Ah, the origin story.
Part of it, yeah. His work significantly sped up information processing and was a direct, crucial step toward modern computing. And that concept of punched cards, as we noted with Babbage, has that even older history in controlling textile looms. Fascinating link.
Okay, so fast forward a bit. World War II. A time of immense need, obviously, spurred this massive demand for computational capacity, especially for military stuff.
Absolutely. Code-breaking ballistics calculations.
Which led to independent innovators in different countries developing early computers, often without even knowing about each other's work, right?
Exactly. Over in Germany, you had Konrad Zuse. He built the Z1, which was mechanical. And then, crucially, in May 1941, the Z3.
And the Z3 was.
The Z3 is generally considered the world's first working, programmable, fully automatic digital computer. Well, electromechanical, really. It used about 2,600 relays.
Relays like telephone switching tech.
Yeah, basically electromagnetic switches.
Yeah.
And it was controlled by punched 35mm film stock, like movie film.
That's ingenious.
He even developed Plancalco, which was arguably the first high-level algorithmic programming language around 1945-46, though it wasn't implemented then. Zuse himself was pretty humble about it, later saying something like, well, I guess it took many inventors besides me to develop the computer as we know it nowadays.
Nice quote. Meanwhile, back in the U.S.
Howard Aiken at Harvard, working with IBM engineers, completed the Harvard Mark I in 1944. Another massive electromechanical machine used heavily by the U.S. Navy during the war.
The one Aiken was disappointed Babbage hadn't finished.
Well, the one he built, yeah, after seeing Babbage's unfinished work. And we also can't forget the Atanasoff-Berry computer, the ABC.
Right, the ABC.
Built between 1937 and 1939. It wasn't programmable in the general sense, but it was the first binary digital electronic computing device, intended specifically to solve systems of linear equations. Another important precursor.
Okay, so we've got these mechanical marvels, early electromechanical steps.
Yeah.
The true electronic revolution really starts accelerating during WWII. How did code breaking push things forward?
Well, the British were absolutely desperate to decode German Enigma ciphers. This urgency led directly to the development of the British Colossus machines.
Built by Alan Turing and his team at Bletchley Park.
Turing was key, yes, along with Tommy Flowers and others. The first Colossus was working by December 1943. These were incredibly fast, special-purpose electronic machines using about 1,800 vacuum tubes.
Vacuum tube, so fully electronic, no relay.
Fully electronic. It could process 25,000 characters per second, which was just staggering then. Absolutely vital to the Allied war effort, reading high-level German communications.
Astonishing speed, and for such a critical purpose. But Colossus was special purpose, right, for code breaking.
Correct.
The next major leap was truly general purpose. ENIAC, the electronic numerical integrator and calculator.
ENIAC, yeah. Designed by John P. Eckert and John W. Mauchly at the University of Pennsylvania. Completed in 1946, also spurred by WWII needs, mostly calculating artillery firing tables.
And the specs on ENIAC were just wild, weren't they?
Oh, completely. Impressive, but cumbersome. ENIAC housed, get this, 18,800 vacuum tubes.
18,000.
Weighed 30 tons. Took up 1,500 square feet of floor space, and it needed a whopping 150 kilowatts of power.
Enough to dim the lights in Philly, apparently.
Probably. Despite its size, it was fast for its time, 500 additions or 300 multiplications per second, but programming it initially, that was something else.
The wire your own technique.
Yeah. You literally had to physically plug cables between different units to set up the sequence of operations, like a giant, complex telephone switchboard. Inconvenient, required a complete rewiring for each new problem, but it was incredibly efficient for the specific programs it ran once set up.
Sounds like a monumental task just to change what it was doing. But there's that great story that illustrates its power, calculating pi.
Oh yeah, that's a classic. ENIAC computed pi to 2,000 decimal places in just 70 hours.
And in doing so.
It revealed that a manual calculation done back in 1846 by a guy named William Shanks had an error way out in the 528th decimal place.
Huh. Take that, human calculator. What do you think that specific moment, proving a human error with a machine, meant for how people saw these emerging thinking machines.
I think it was a powerful validation, definitely. It probably started to shift public perception, from these things being just fancy calculators to being truly reliable, even superhumanly precise instruments in some ways.
Right. But despite ENIAC's power, the real game changer conceptually was still to come, the stored program concept.
Absolutely. Enter the brilliant mathematician John von Neumann. He got involved with the ENIAC team, became fascinated by it, and in 1945 undertook this abstract study of computation.
And his big idea.
His revolutionary proposal was that a computer should have a simple, fixed physical structure, no more rewiring for every problem, yet be able to execute any kind of computation just through properly programmed control.
And crucially, he recommended using the binary system, those zeros and ones from Boole, for storage.
Yes, much more efficient electronically.
And most importantly, proposed that both the instructions and the data should be stored within the same memory unit.
That was the seismic shift, the stored program technique.
How did that fundamentally change everything?
Oh, in so many ways. It allowed for conditional control transfer. The program could jump around, make decisions based on results, stop, restart at any point.
Like Babbage envisioned with his looping cards, but electronically?
Exactly. And even more mind-bending for the time, instructions themselves could be treated like data. They could be loaded, stored, even arithmetically changed during computation.
Wow.
This made computing and programming infinitely faster, more flexible, incredibly efficient. You could have standard routines, subroutines kept in libraries and just load them when needed instead of wiring them up every single time.
That's truly revolutionary. That sounds like modern computing.
It's the foundation. So the first generation of modern programmed electronic computers, built in the late 1940s, like EDVIDI and EDSAC, all adopted these improvements, led directly to machines with random access memory, or RAM.
And this brings us to UNIVAC, the commercial breakthrough.
UNIVAC was one of the first commercially available computers, delivered to the U.S. Census Bureau in 1951. But it really achieved widespread fame for that amazing public demo.
The 1952 election night.
That's the one. On live television, UNIVAC accurately predicted Dwight D. Eisenhower's landslide victory based on early returns.
And the TV guys didn't believe it.
The CBS News team was totally skeptical. They thought the projection was impossible based on traditional analysis. They even hesitated to announce it, but UNIVAC was right. It astonished everyone and made UNIVAC a household name overnight.
Okay, so the journey from these huge room-filling behemoths like ENIAC and UNIVAC to the sleek devices we carry today relied heavily on something we totally take for granted now, miniaturization.
Absolutely essential.
So how did that process kick off?
It really began with the invention of the first working transistor at Bell Labs in 1947.
By Shockley, Bardeen, and Bratton. Nobel Prize stuff.
Exactly. This was an immense breakthrough because transistors were so much smaller, way more reliable, and vastly more energy efficient than those bulky, hot, power-hungry vacuum tubes.
What a pivotal invention. Transistors led pretty quickly to things like portable transistor radios in the late 50s, right?
Yeah.
People could hold a radio in their hand that used to be like furniture.
Precisely. Then came the next big step, the integrated circuit, or chip.
Putting multiple transistors onto one piece of silicon?
Yep. Federico Faggin at Fairchild Semiconductor, and later Intel, was key here. He developed the first commercial integrated circuit in 1968, which led directly to the first single-chip microprocessor, the Intel 4004, around 1969-1970, an entire CPU on one tiny chip.
And this kind of relentless miniaturization brings us to a really foundational concept in the industry. Moore's Law.
Ah, yes, Gordon Moore's observation. It's not really a physical law, more like an empirical observation or prediction he made back in 1965.
Which dates?
That the number of transistors you can cram onto a microchip roughly doubles every 2 years while the cost goes down.
And it's held remarkably true for decades.
It really has. This has consistently driven increased computing power and significantly falling costs, shaping the entire trajectory of technological advancement we've seen.
So with these smaller, more powerful, cheaper chips, the stage was set for the personal computer revolution.
Definitely. Things started heating up. April 1977 was a really pivotal moment with the introduction of the Trinity, the Apple II, the Commodore PET, and the Tandy TRS-80, all aimed at consumers and hobbyists.
But the real game changer for business and standardization was the IBM PC, wasn't it? Introduced August 1981.
Yeah, the IBM PC was huge. IBM, this giant trusted company entering the market, gave personal computers massive legitimacy. And crucially, they cooperated with a young Bill Gates and his fledgling company, Microsoft, for the operating system MS-DOS.
That partnership, pretty significant.
Understatement. That collaboration, plus the powerful IBM brand and their open architecture decision letting others clone it, made the IBM PC the de facto standard.
It just exploded. It immensely expanded computer use and sales, with IBM and IBM compatibles dominating the early PC market.
Yep. Even though IBM eventually sold its PC business to Lenovo back in 2005, its influence in standardizing the PC architecture was absolutely immense.
And it's worth remembering, these early personal computers weren't like today's machines at all. No friendly icons or mouse clicks initially.
No, not at all. You were typing cryptic commands on a black screen with green or white text, the command line interface. Before graphical interfaces became common, that was how you interacted.
Speaking of powerhouses, though, let's not forget mainframes. They didn't just disappear when PCs arrived.
Oh, absolutely not. Mainframes originated back in the 1950s, primarily with IBM, and they were initially just colossal room-filling machines. Absolute beasts. They quickly became synonymous with enterprise computing, handling vast amounts of critical business data.
Batch processing, databases.
Exactly. They evolved through the 60s and 70s as these critical enterprise solutions. The 1980s brought rapid advancements with microprocessor design influencing them too, and IBM's ZOS operating system really solidified their role.
And they're still around today, right? Though maybe not quite room-sized anymore.
Definitely still around, and still crucial for many large organizations, banks, airlines, insurance companies. But yeah, much smaller now, maybe the size of a large refrigerator. And the cost is down to maybe around $100,000 for an entry-level one, a far cry from their multi-million-dollar price tags of the past.
What's truly remarkable is how relevant they still are. These modern mainframes are incredibly versatile, aren't they? They can blend cutting-edge stuff like Linux virtual environments
Yeah, running Docker containers on Linux using ZVM.
right alongside traditional business systems, maybe running COBOL code that's decades old, all on the same physical hardware.
It's pretty amazing. An IBM Z15, for example, can handle something like 1 trillion web transactions a day. Their capacity and reliability are still unmatched for certain workloads.
Okay, so from mainframes back to the personal experience. One of the most visible changes in how we interact with computers was the graphical user interface revolution, the GUI.
Right. Using graphic icons, windows, menus, and a pointing device, usually a mouse, to control the computer, based on what's often called the WIMP paradigm. Window, icon, menu, pointing device. Much more intuitive for most people than the command line.
And the stage for this was set pretty dramatically way back in 1968 by Doug Engelbart, the mother of all demos.
Oh, legendary stuff. Engelbart publicly demonstrated a mouse which he invented, along with hypertext, networked collaboration, word processing, video conferencing, basically showing a future of computing that was decades ahead of its time. Mind-blowing demo.
And his work directly influenced the researchers at Xerox PARC, right? Palo Alto Research Center.
Hugely influential. In 1973, Xerox PARC developed the Alto personal computer. It wasn't a commercial product, more of a research platform, but it featured a bitmapped screen and really demonstrated the power of the desktop metaphor and the GUI.
Lots of future tech leaders saw demos of the Alto.
They did. It became this legendary machine that heavily influenced future designs.
And then Apple famously stepped in.
Yeah.
Steve Jobs saw the potential at PARC.
Famously, yes. Jobs and the teams at Apple Computer took those PRX ideas, refined them, and developed them further into the Apple Lisa in 1983, which was innovative but commercially unsuccessful.
Too expensive.
Way too expensive. And then, crucially, the commercially successful Macintosh in 1984.
Which really popularized the GUI for the masses.
Exactly. The Mac brought the desktop metaphor with those easy-to-understand icons you could click and drag to a much wider audience. In fact, Apple later famously brought that look and feel copyright lawsuit against Microsoft over GUI similarities in Windows.
Right. Speaking of Windows, Microsoft's Windows 1.0, released in 1985, it wasn't an immediate hit, was it?
No, it had a pretty slow start. It ran on top of DOS, felt a bit clunky. But Windows 3.0 in 1990, that was the one that really popularized GUIs for the huge IBM PC-compatible market, made PCs much more accessible.
And the Windows 95 in 1995.
Huge launch. Windows 95 integrated MS-DOS and Windows properly, had a major GUI redesign with the Start button and taskbar. And its massive market success really cemented Microsoft's dominance and kind of sparked the browser wars, with Netscape Navigator being bundled initially.
It wasn't just Apple and Microsoft in the TI game, though, right?
Yeah.
There were others.
Oh, yeah, definitely. The Amiga Workbench, launched in 1985, was very advanced for its time, known for its true preemptive multitasking capabilities. And RISC-OS in 1987 for Acorn computers was actually the first operating system to feature anti-aliased fonts system-wide, making text look much smoother on screen.
Little details that make a difference. And today, GUIs keep evolving, right? Mobile devices like the iPhone and iPad really popularized multi-touch interaction.
Yeah, moving beyond the traditional WIMP, sometimes called post-WIMP interfaces, gestures, direct manipulation, and even on desktops, there's been a trend toward more 3D effects, transparency, smoother animations, and window management.
Okay, so we've talked hardware, the machines themselves, how we interact via GUIs, but what about the actual language computers speak? The code.
Right, the software side. At its absolute core, computers operate using binary code, just zeros and ones.
Fun enough.
Exactly. Representing an on or off state in an electronic switch, or maybe higher versus lower voltage. And this concept, as we mentioned earlier, goes right back to George Boole's true-false algebraic logic from the 1800s.
It's funny, we humans typically count in base 10, using 10 digits 0 through 9. But computers using binary only have 2, 0 or 1.
And somehow, everything you put into a computer gets translated into this fundamental on-off code.
Everything, like colors, shapes.
It's everything. From the colors in an image, every single pixel, to the shapes on your screen, every letter you type, every note in a song. It all gets represented as sequences of zeros and ones, often using standardized systems like ASCII or Unicode, where specific patterns of bits represent specific characters, numbers, or symbols.
Okay, so how does the code that humans write, say in Python or C++R, actually become those zeros and ones that the computer understands and acts on?
Good question. So, when a programmer writes code in a human-readable language, it needs to be translated. This happens in one of two main ways. It's either compiled or interpreted.
Compiled means?
Compiled languages like C or C++ or Fortran are run through a program called a compiler before you run the software. The compiler translates the entire program into machine code, those low-level zeros and ones instructions the CPU understands all at once. This resulting machine code file can then be executed directly by the computer.
And that's generally faster.
Generally faster at runtime, yeah, because the translation work is already done. But it can sometimes be a bit harder to debug because you're dealing with that compiled output.
Okay, and interpreted.
Interpreted languages like Python or JavaScript, or older languages like BASIC, work differently. They use an intermediary program called an interpreter. The interpreter reads the human-readable code line by line or statement by statement and executes it directly, translating on the fly.
So, easier to debug maybe, but slower.
Generally, yes. Easier to debug because you can often pinpoint errors to a specific line of the original code, but it can be slightly slower because that translation step is happening during execution. Though modern interpreters are very sophisticated and often use techniques like just-in-time JIT compilation to speed things up.
But regardless of compiled or interpreted, the end result is getting instructions to the hardware.
Exactly. It all gets translated down into machine code, those very low-level instructions that directly tell the computer's processor, the CPU, what specific operations to perform on data. Add this, move that, compare these.
And the speed at which this happens is just hard to comprehend.
It's mind-boggling. A single modern CPU core can execute billions of instructions every second. Billions.
Wow. Now, when programmers are writing this code, are there different ways they structure it, different philosophies?
Yeah, broadly speaking, there are different programming paradigms. Two main ones you hear about are procedural programming and object-oriented programming.
Procedural is?
Procedural programming is kind of the traditional approach. Think of it like a recipe. A straight list of logical, step-by-step instructions for the computer to follow in order. Languages like C, Fortran, COBOL are typically used this way. Very direct.
Okay, and object-oriented?
Object-oriented programming, or OOP, thinks about things differently. It structures code around objects which bundle together data and the functions that operate on that data. Think of creating reusable blueprints, called classes for things, and then creating specific instances, objects, from those blueprints. Languages like Java, C++, 2Python, C# heavily use OOP concepts.
And the advantage there is?
It can make code more modular, reusable, and easier to manage, especially for large, complex software projects. You can build things out of these self-contained objects.
Okay, so this ability to write code, whether procedural or object-oriented, is obviously incredibly valuable today.
Oh, immensely. There's incredibly high demand for skilled coders, software developers, programmers, whatever term you use, across virtually all industries, not just tech companies. Finance, healthcare, entertainment, manufacturing, everywhere.
High demand usually means good opportunities.
Definitely. It's a field with a lot of job openings and often significant earning potential, reflecting just how crucial these skills are to our modern economy and society.
And with that demand and the importance of software comes immense responsibility, right? The criticality of good code.
Absolutely critical. Think about it. Our lives increasingly depend on these thinking machines and the code that runs them. Self-flying planes, self-driving cars are coming, robotic surgery systems, complex financial trading algorithms, artificial intelligence.
Yeah, the stakes are high.
Incredibly high. Reliable, well-written, thoroughly tested, secure code is absolutely essential to ensure these technologies work as intended and, crucially, safely. Bad code can have very real, very serious consequences.
Now, shifting gears slightly, there's a common misconception about computing, especially as it grew into this massive industry, the idea that it's always been, a male-dominated field.
Right. And the historical reality, particularly in the very early days, is actually quite the opposite. Computing, especially the programming side, actually began as a largely female-dominated profession. There's a disproportionately large female workforce doing the early programming work.
That's a truly surprising insight for many people, I think. We already talked about Ada Lovelace, who's rightfully recognized as the first conceptual programmer, providing those theoretical underpinnings way back.
A true visionary.
But there were so many more women involved in the practical implementation later on. You mentioned Grace Hopper earlier.
Admiral Grace Hopper, an absolute legend. She made huge contributions working for the U.S. Navy during WWII on the Mark I, then later worked on UNIVAC. She was instrumental in the development of early compilers, the programs that translate human code to machine code, and championed the idea of machine-independent programming languages, leading to COBOL.
And she famously popularized the term debugging after finding an actual moth causing problems in a relay on the Mark II computer.
That's the famous story, a literal bug in the machine. She also did a huge amount to support youth education and computing later in her long career. A real pioneer.
And what about the women who actually programmed ENIAC? You mentioned it was initially programmed by wiring it up.
Yes, the original ENIAC programmers were a team of 6 women: Kathleen McNulty, Frances Bell-Les, Betty Jean Jennings, Elizabeth Snyder, Marlon Westkoff, and Ruth Lichterman. All held degrees in mathematics.
And their role wasn't initially seen as professional.
Initially, no. They were often called computers or operators, and were told they couldn't even earn professional ratings. But during World War II, with many men away, women were compelled into these critical calculation and programming leadership roles. It was only later, in November 1946, after their crucial work was undeniable, that they obtained professional evaluations. They were essentially figuring out how to program this entirely new kind of machine as they went along, working from wiring diagrams.
Incredible pioneering work, basically inventing the practice of programming on the fly. So if women were so central to the early days of programming, what happened? Why the shift?
It's a really striking historical shift and kind of a complex sociological one. The gendering of computers changed dramatically over time as computing moved from a more niche, scientific, or clerical task to a high-status, economically powerful industry.
It got reframed.
It got reframed, yeah. It started being marketed and perceived as a more male-suited profession, requiring certain kinds of logical or mathematical aptitude that became stereotypically associated with men. This coincided with and was reinforced by changes in hiring practices, educational pipelines, and even media portrayals.
Leading to fewer women participating.
Exactly. A significant decrease in women's participation, particularly from the mid-80s onwards in computer science education, and the unfortunate rise of these negative stereotypes. Women were often unfairly portrayed as less interested or less capable, which of course wasn't true, but the cultural perception shifted.
That's a real loss of talent looking back.
A huge loss. Thankfully, there's been a growing recognition of this history and concerted efforts in recent years to address the imbalance.
Like what?
Well, you have things like the UN designating February 11 as the International Day of Women and Girls in STEM to raise awareness, and numerous nonprofit groups like Girls Who Code, founded by Reshma Sarjani, are actively working to close the gender gap in tech, encourage young women, and provide them with skills and mentorship.
And are these initiatives working? Are there examples of real change happening?
There are definitely success stories, particularly in academia, showing that changing the culture around computing is key. Harvey Mudd College is a famous example.
What did they do?
Under their president, Maria Klaw, who's a computer scientist herself, they make some interesting changes. They famously renamed their introductory computer science course from something generic like Intro to Java to Creative Problem Solving in Science and Engineering using computational approaches.
Framing it differently.
Exactly, making it less intimidating, maybe more appealing to students who didn't already identify as coders. They also created a second introductory course specifically for students with no prior programming experience, splitting them off from the experienced students initially. And they really emphasized teamwork and collaboration in projects to combat that stereotype of the lone male programmer working in isolation.
And the result?
Dramatic. The proportion of women majoring in computer science at Harvey Mudd jumped significantly, reaching around 40–50%, way above the national average.
Wow. Any other examples?
Carnegie Mellon University also saw success with reforms. They made their computer science applications look for broader qualities, like leadership and teamwork, not just top math and science scores. They also established a supportive women's computer science club.
And that helped too.
Yeah, their percentage of female computer science majors also rose significantly, exceeding 40%.
So the takeaway here is that it's not about inherent differences, it's about the environment.
Exactly. These cultural approaches focus on changing the environment, the teaching methods, the messaging, and breaking down stereotypes. They operate on the principle that interest and ability aren't inherently gendered, but are heavily influenced by culture, encouragement, and opportunity. It's about creating an inclusive culture where everyone feels they belong and can thrive.
That's a really important point. So as we bring this deep dive kind of full circle now, it's truly incredible to reflect on the whole journey we've traced.
It really is.
From Charles Babbage's visionary, but ultimately mechanical, dream of a thinking machine,
Years and levers.
to the unbelievably complex electronic marvels we hold in our hands today, and the invisible, intricate code that powers literally our entire modern world.
Absolutely. It's just such a testament to human ingenuity, isn't it?
Right.
And persistent collaboration, building on ideas over generations, even with those gaps and reinventions, and constant evolution.
Understanding this history, I think, really gives you a much deeper appreciation for the devices you use every single day. You realize how fundamental concepts like binary logic from Boole or the stored program concept from von Neumann continue to underpin absolutely everything.
From your smartphone to the massive mainframes humming away in data centers running the cloud, it's all built on these foundations.
So here's a final thought to leave you with. Considering the cyclical nature of technology, how ideas often get reinvented or adapted decades later, like you see parallels between early centralized computing and today's cloud computing.
History repeating itself in new forms.
Right. What seemingly insurmountable technological challenges of today might be solved in completely unexpected ways, or maybe even reinvented by future generations looking back at our efforts.
That's a fascinating question. And as code becomes even more integral to our lives, maybe even reaching a point where AI starts writing significant amounts of new code itself, how might our relationship with these thinking machines continue to evolve?
It's a truly thought-provoking place to end, isn't it? Where does this incredible journey take us next?